Hi there. This video will see an example of designing a beam, considering now that we know about principal stresses. So we have seen an example before designing a beam based on flexural stresses, and we consider mainly the extreme points, the top points, and the top and the bottom points. But now we'll see how principal stresses will impact the process we have seen before. So we have here a beam that's simply supported span here AB with a cantilever BC with the shown distributed load and point load at C. The beam is made by is made using a steel cross section, a wide flange 14 by 26, and from the tables we got the moment of inertia to be equal to 245 inch to the power 4. And we want to find the maximum principal stress that's developing in this beam. So the first thing you need to think about is where is really the critical section here. So to find the critical section, you have to do statics. So start with statics, finding reactions. We'll not go into the statics in details, but we have to do them to be able to do a strength of materials analysis that we'll do. So considering these reactions, then I will draw my shear and moment diagram. So this is the shear. You start from the left, you go up by 20, and you go down by the distributed load linearly here. 4 times 12 is 48 kips foot. That brings us from 20 to 20, positive 20 to negative 28. Then you have the reaction 36 will jump us to positive 8, and then you go straight until you hit 8 kips load at C, which will bring us to equilibrium. And then you use the shear diagram to draw the moment diagram. And we see here an intersection, the zero intersection of the shear diagram. That's where the maximum shear moment of positive 50 kib foot. That's where it happens. And then it goes down all the way to negative 48. And then we'll go to 0 at point C. So the question here is, which section here is more critical? I see there's a positive 50, but it comes with 0 shear. And see at point B, there's negative 48, but it comes with the biggest shear force here, which is negative 28. So which one is more critical? Knowing that principal stresses, a combination of normal and shear stress can result in a principal stress that's larger than the provided initially normal stress. So by looking and observing, I see here that the moment values between section 1 and 2 are not that different. Like 50 and 48, the magnitude of the values is not that different. But section 2 comes with a big shear force here. So kind of having that intuition that section 2 will be more critical than section 1, and we'll analyze it. And then later we can check section 1 if it has really developing here the maximum normal stresses. So we'll focus initially on section 2. And when we looking at section 2, we'll analyze within section 2 two critical points like we have seen in the previous video in wide flange and sections in general that have change in the width, dramatic change in the width of the section. We will have to analyze the top or the bottom points, extreme where the flexural stresses happen, and also the point where the transition from the width here of the section have a transition, which is basically the junction of the web and flange. So we will analyze each one of these, analyze the stresses, shear and normal stresses developing, and the resulting principal stresses. So here, point D, I look at point D, there are both the normal stress and shear stress develop, and we covered that in the previous video, so we'll not explain it in detail, but point D is not the extreme point in terms of flexural stresses, but it's really far from the centroid, so it's not MC over I, it's negative MY over I. And then tau we covered and explained in the previous video that in wide flange, tau would equal to roughly V over A web. and A web is equal to T, the thickness of the web, times the depth of the whole section. So if I start with sigma D, so it's negative M, which is a negative value of negative 48. Bring that to from kip foot to kip inch to match it with the area properties I have. And then this is times the distance y coordinate of D, which is 6.535 inches from the centroid, divided by I. And that will bring us here sigma D to be positive 15.36 ksi. And then we'll calculate tau, which is the V divided by the area of the web. And you see here the area of the web, the thickness of the web is 0.255 inches. And then the height of the whole section is double the height from mid of the centroid, which is equal to 6.535 plus the thickness of the flange, 0.42. Add these together, double, that's the full height of the section, and times the thickness of the web, that's the area of the web. So we'll end up here with tau is equal to 7.89 ksi. So when I draw this stress block of this, if you look at mainly the right side of the stress block, so the right side of the stress block, this one, this is the face of the block that corresponds to the face of the cross section. So I have sigma x and I have tau xy. So sigma x here is the one we calculate, and sigma y is equal to 0. So when I plot now these 2 points, sigma x with negative tau xy and sigma y and tau xy, that will give us the diameter of the circle, or Mohr circle, and this will be the center of it, sigma average, and we can see here that the principal maximum stress at D will be the intersection of the circle with the sigma axis. And to be able to find it, I have to calculate the 2 main properties of Mohr circle that I will always have to calculate, which is the center of the circle, sigma average. So sigma average is the average of sigma x and sigma y, and then the r, the radius of the circle, which is square root of sigma x minus sigma y over 2 square plus tau square. And now I can say that sigma max D is equal to sigma average plus R. And that will bring us a value of sigma max D to be 18.69. So we can see the principal maximum stress here is larger than the normal flexure stress sigma D. And this is why principal stress is very critical. Shear stress can actually magnify the normal stress that's initially given to us and provide a larger normal stress, principal stress, at a different orientation. So we're not interested to know really the orientation of that sigma max D. It's at theta p. So we're not after really the orientation, we're after the magnitude of the maximum normal stress. So that's enough for analyzing this point D. Now next would be point E. And point E is at the top of the beam, so it's now at C distance, MC over I. That will be the stress at E. And I know that tau is equal to 0 because the Q uppercase, if you think about tau is equal to VQ uppercase over IT, Q uppercase is equal to 0. So that will be the stress block here. Only one stress, sigma x, and sigma x is equal to sigma m at E. Sigma y and tau xy would be equal to 0. So when you draw the Mohr circle for that stress block, and it will be a diameter in the Mohr circle of stresses at this point, and you can see here that sigma max or sigma 1, maximum principal stress, is exactly sigma m. There is no change, there is no transformation of stresses because there is no tau. So my maximum normal stress here will equal be basically to maximum flexure stress. So applying the formula and considering now the only thing I'm changing here is the distance. So instead of only 6.535, which is the point D, now I'm adding that thickness of the flange, and we'll end up here with maximum principal normal stress to be 16.35. Comparing that to sigma max D, I can say now that the maximum principal stress in the beam at this section 2 would be equal to the maximum principal stress at point D, which is 18.69 KSI. Now, let's go back to the big picture. I had initially two sections, section 1 and 2, and I kind of had that initial hunch, you can say, that section 2 will be larger and will be more critical because it will have pretty close moment values to section 1, but a large value of shear stress, shear force. So now let's reconsider section 1. I know that there is no tau because V is equal to 0, so sigma M will be the value for sigma maximum principal stress at this section, the top and bottom points of that section. So it will be look similar to sigma ME, but I'm just plugging in the other moment value of 50 kip foot, and I will end up here with a value that's bigger than sigma ME. Yes, but still it's less than sigma max D. So here, that's a clear example of transformation of stresses that brings us principal stresses that are not given directly from the cut we make and the loads we have will be critical and will govern our design. So in this case here, the maximum principal stress is happening at a point, the junction point of the web and flange, point D, at section 2. So that's the end of this exercise. We got really what we want. Just pay attention to, first, given a beam, you have to find the critical section in the beam. In our case here, it was kind of a clear call. One section had both moment and shear values pretty large, so we went with that, and then we went back and checked the other section. And within the section, you have to analyze 2 points if you're dealing with a wide flange section. Of course, if it's a rectangular section, you don't have to really worry about principal stresses like we explained in the previous video. All right. Thanks for watching. I will see you in the next lesson on combined loads. Take care of yourself and with those around you. Thanks so much. Bye.